Okay, so I am covering permutations. So, what exactly is a permutation? So, the number of ways, say you've got a group of items, like you've got 5 pieces of fruit and you're arranging them in a line. The number of ways you can do that is called a permutation. What's very specific about a permutation is that the order that things are picked matters. So if you had a group of fruit, if I pick an apple first and then an orange is different from an orange and then an apple. So the order matters.
Okay.
And this often gets confused with combinations because combinations, the order does not matter. Now, if you see the word combination in a word problem, that does not always mean you're doing a mathematical combination. Sometimes you're doing a permutation because the word combination has its mathematical definition and then it has its everyday definition. And so the word combination, a word problem usually means the everyday definition where you just have things that you're putting in, you're just combining together. But it doesn't necessarily mean it's always a combination. It could be a permutation. The question is, does order matters? So just a heads up on that. Because there is a particular problem on the assignment where it says combination, but it's actually a permutation because the order matters. So the key thing about a permutation that's different from some of the counting problems that we've done. So the simple counting problems, you're just saying, well, how many of this can I choose from? Like, if you're doing a license plate and you have different letters that you can choose from or different numbers, you can reuse letters in a license plate. In permutations, you cannot reuse something. So once it's picked, it's no longer available to be picked again. So the order that things are picked matters and they don't get reused.
That's a permutation where it
Yes,
doesn't get reused.
that's
That's
correct.
the key. That's the key thing I was looking for. Okay.
Yes, yeah.
Okay.
So you're using permutations. The first thing is, does order matter? The order that you're picking them, does that matter? And then are you repeating them? Because if you're repeating them, you can't use a permutation.
Okay.
So the first thing is just the total number of permutations, which I have in parentheses, ordered combinations, because it's a combination, but they're ordered. So that's why the word combination does not necessarily use mathematical combination. Question is it ordered or unordered? So the total number of ways that you can basically group things in a specific order is the total number of permutations, and that's by doing the factorial. And so the factorial is basically the exclamation mark is what we use to have a factorial, and you're just counting down however many numbers you have, and then you just count down from there. So if you have 6 things that you're grouping, you're just doing 6, then 5 times 4, and you just count all the way down. And that's because you can't reuse them. So if there's 6 choices in the first spot, I can't reuse the one that I picked. So now there's only 5 left. Now I've picked 2 of them, so there's only 4 left. So as you're trying to order these 6 objects in 6 different spots, your choices decrease as you place each one. And so that is why the numbers are going down. And so that gives us the factorial. So that's the total number of ways that you can put something in order is the factorial. So I've got 2 examples here. We have 4 couples. They reserve seats in one row for a concert. And how many different ways can they sit when there are no seating restrictions? So the no seating restriction means that we're not like forcing couples to sit next to each other. Like they can just sit wherever. But the order that they sit matters, because you can, if you have a certain number of seats, you know, that each seat has a different number to it. It's not, they're not all just the same seats. So the order that they're seated matters. So order matters here. And of course, somebody can't have more than one seat. They can't be reused. So this is a permutation. So if we've got 4 couples, we actually have 8 people that we're trying to seat. And so the answer to this is 8 factorial. And so this is not something that you would want to, I mean, you could just do it on your calculator, 8 times 7 times 6 and so on, but it's just a lot easier to use the factorial button if you have it on your calculator, or if, I know Desmos has the ability to do that. It will just save you a lot of time than trying to, you know, actually calculate it by hand. And you don't have to even write it out. You can just say 8 factorial and then put the number, which is 40,320. So if you've got 8 people and you're trying to sit them, and there are 40,320 different ways that you can do that. A lot of different combinations of seating arrangements. Now, if we had asked, you know, if we wanted couples to stay together, that would be a different situation. And then there would be fewer possibilities here, but we would not be able to do a permutation because now we can't just count down. We have more restrictions that we have to think about. Now, the second example I have here is in how many ways can 6 people sit in a 6-passenger car? So again, you can't reuse some only, each person only gets 1 seat, and order matters because, you know, the front seat is different from like the middle or the back seats, you know. If you tell any kids the where they're sitting matters, there's fights over the specific seat. So the different seats matter. So this is just 6 factorial. So again, I'm just going to do this on my calculator. And that comes out to 720.
So just the math behind that, the 6, that's the 6 times 5 times 4 times 3 times.
Yes.
Okay.
Yeah. So if you did that on your calculator, which it'll help if I didn't actually miss a number, but you could actually, it will give you 720.
Okay. Sorry, I just like to know the math behind it.
Oh, that's fine.
I mean, the function,
good.
the function is great, but
Yeah.
why is it? Why, somebody comes up, well, why is that? And then it's because the calculator told me so.
Right. Yeah. I mean, as long as you understand, well, this is, you know, what it's doing, why it works that way, you know, looking at this is like, okay, if you do it with small problems, you can understand why that's the pattern, you know.
Right.
But if you try to do it with a big problem to describe the pattern, it'd be really confusing. So the next part about permutations is, let's say you don't want to order everybody. You want to order a small subset of them. So like, let's say you have 8 couples, but for whatever reason, maybe, or you have 4 couples, maybe only 3 of them went to the show instead of 4. And so now you only need to order 3 couples versus the 4 couples. And so you're not taking the full group. So it's still permutation, but we're taking a subset of them. And so we use N to represent the full number of items we're choosing from. And then R, which is the smaller group that we're trying to form. And so we use P because it's a permutation. And it's NPR. And a lot of people in their head, my Google thinks I'm talking to that. Didn't say Google. But in your head, when you read NPR, some people say N pick R, or like 5 pick 2. You've got 5 things and you're picking 2 from there. And they use the word pick for permutation. No, again. Combinations use a C, so usually people will use the word choose to stand for C. but it's our abbreviation here is NPR, which I actually have an announcement that I posted, I think it was Saturday, about the various ways to attempt to type that, because it's not something that, like, if you try to type up your work, it's very difficult. It's a lot easier to maybe just do it by hand.
I saw that, yes.
Yes. Yeah, and it took me a while. I was actually really upset because I had this whole announcement and I typed it up before the week began and I had it all set to post on Friday. And then come Saturday, I'm like, why is that announcement not there? Somehow it got deleted and I had to rewrite the whole thing. And I'm like, now I have to figure out again, how did I do all that? So,
Oh my gosh.
yeah. So we use NPR. And so the first number is always the total that you have. And then the second number there is how many your subset. And so you've got your n factorial, the total number of combinations. And then because you're only choosing a subset of those, there's going to be fewer of them. So you divide it by a number to get a smaller number at the end, because there's not going to be as many choices. And so it's n factorial divided by n minus r factorial. And what happens if you try to expand this out, and I'll do it with 5, whoops. 5, why is my pen not writing? I had this problem a couple days ago. Let's see. Oh no. Okay, we're gonna try to write with my mouse. This is not gonna be
Good luck with
fun.
that.
Yeah. Oh, wait, I can, do I? Oh,
It looks like it was writing, it was just white.
yeah, I don't know why the ink was right. Okay. Because I was looking at that. I'm like, wait a minute, I see a little bit of white there. Very strange. So we've got 5, pick 2. And so you've got your 5 factorial on top. And then it's 5 minus 2 factorial on the bottom. So when we simplify this, I've got 5 times 4 times 3 times 2 times 1. And then 5 minus 2 is 3 factorial. So we've got 5 times 4 times 3 times 2 times 1. And then 3 times 2 times 1. So what happens is these things kind of cancel out. So it's like you're doing the factorial, but you stop at a certain point. You're not doing the full factorial because it cancels out. And this formula makes sense because if I'm picking 2 things and I have 5 to choose from, I've got 5 choices and I'm not reusing it, then I have 4 choices, but then I'm not picking anymore. So it would just be 5 times 4. So the formula that we have here makes sense if you think through, I'm picking 2 things out of a group of 5, and those are my choices. But having a formula is nice because you're not going to want to try to do a counting problem kind of thing by hand when you have really big numbers. The formula will do it for you.
Right.
So that's what this formula is doing. It's just, you're, instead of doing using everyone, you're just stopping at a certain point. So we're just going to practice doing these. And so 6p5. So it's 6 factorial over 6 minus 5 factorial. So 6 factorial we've done. We found that was 720. And then 6 minus 5 is 1. So that's 1 factorial. And 1 factorial is just 1. So we're just doing 720 here over 1. So we just get 720. So the number of ways to choose 5 out of 6 is 720.
Okay.
So now, what if we have 6 and we're picking 6 out of 6? So You can get the answer to this if you think through what we've talked about so far.
Well, this tripped me up because when I saw, we can't have a zero in the denominator.
You can if it's 0 factorial.
Yes, you can.
Because 0 factorial is equal to 1. It's a special rule, that little factorial thing. If 0 factorial is equal to 1. So we end up with 720 over 1 again. So we also get 720. So the number of ways to choose 5 out of 6 is the same as the number of ways to choose 6 out of 6. And you might think, well, this doesn't make any sense. But it does, because if you choose 5, and then if you wanted to choose 6, that last spot, there's only one way to do it because there's only one thing left to put there.
Mm-hmm.
So you're not adding any extra combinations. It's kind of forced.
Mm-hmm.
So the number of ways to choose 5 out of 6 is the same as choosing 6 over 6. And if we combine this with what we learned before, our 6 factorial is the same as choosing 6 out of 6 because you're just placing all of them. It basically kind of cancels it out.
Okay.
So just kind of interesting observations there. So if you're doing these permutation things and you're like, wait, my numbers are the same. Expect that you'll have some of the numbers the same if you're doing like 5 pick 4 or 5 pick 5. That's going to happen because it's just, you're kind of forcing that hand. It's an interesting property of permutations. And doing the calculation by hand like this isn't too bad as long as you have your factorial button. But most calculators also have a button that allows you to do the permutation. And so if I was to do like the 6 pick 5, I have to hit on my particular calculator because I have the TI-30. I hit the 6 first, then I hit my button that gets to the option NPR, and then I type my 5, and so that gives me 720. So you can use that shortcut button of the NPR instead of using the factorial and writing it out. But I do encourage you to write out the formula at the factorial and work through it because it helps you kind of see what's going on. And because if you just hit the button to get the permutation, you're not really understanding the calculation that's going on. But
Right.
if you're looking at here, you can see the calculation and you can see, okay, that's why they got to the same thing. You can kind of think through, what does this actually mean?
Right.
So now we're going to apply this to word problems, of course. So a patient with end-stage kidney disease has 9 family members who are potential kidney donors. How many possible orders are there for a best match, a second best match, and a third best match? So we're picking 3 out of 9. So this is going to be 9P3. So our 9 factorials on top. Then we have 9 minus 3 factorial. So it's going to be 9 factorial over 6 factorial. And with small numbers like this, then you can even do the thing where you cancel it out. And this would be equal to 9 times 8 times 7, because anything after the 6 factorial will cancel out. So, I mean, you can even go further and not even do the factorial stuff if the numbers are small enough like this. So knowing that all the 6 factorial stuff cancels and we just do 9 times 8 times 7, this gives us 504. So this type of problem is great for a probability problem because there are 504 different ways this can happen. So what is your probability that a specific ordering is in this specific order? It would be 1 out of 504.
So when you say that it's 1 out of 504,
like let's say your family members, you've got an aunt, an uncle, and a grandfather, and you want specifically in that order, the aunt is the best match, the uncle is the second best match, and then the grandfather's third best match. That is one specific order. And so the probability of that being the order would be 1 out of 504. Because there are 504 possible ways that we could have orderings here.
Okay, okay, yeah, because the question was how many possible orders.
Mm-hmm.
It wasn't.
It wasn't a probability. I just threw that in there to
Right.
kind of connect it to probability.
Okay.
Because there are, the whole reason we're doing these permutations and then later combinations is because when you start finding probabilities, you need to know, well, how many choices do I have in the beginning? And that's where you use permutations and combinations to figure out how many choices you have, which then allows you to figure out the probability later. So, second example, from a pool of 12 candidates, the offices of president, vice president, secretary, and treasurer, so there's 4 of those, need to be filled. And how many different ways can the offices be filled? So we've got 12, and we are picking 4 out of the 12. It's 12 factorial over 12 minus 4 factorial. So it's 12 factorial over 8 factorial. So instead of doing the canceling out method, I'll just do the factorials this time, just for something different. So this may be one where you might be like, well, maybe I don't want to write out my factorials, because you see I got a very big number for 12 factorial.
Yes, we did.
An 8 factorial. I've seen this number before. So you have to start keeping track, like, oh man, hopefully I don't lose numbers when I'm doing this calculation. If you get a decimal, that tells you you made your calculation wrong, you typed a number wrong, because these should always come out as whole numbers. So it's 11,880. Or if we did, instead of doing the factorials, it'd be 12 times 11 times 10 times 9. Man, my phone really, I even have my phone on silent, but apparently when Google thinks I'm talking to it, it does not want to go on silent. But you would get the same answer if you did 12 times 11 times 10 times 9. And I'm going to just verify to make sure my calculation is correct. Yes. And so once you start getting larger numbers like this is where you might want to stop using the factorial notation and just use the permutation button, because you're going to start getting really, really large numbers, and then you're not going to want to write those down. Okay, so this is the last type of permutation we have, and this, I think, is kind of the hardest one to just figure out and use. So it's a total number of distinguishable permutations. So this is specifically if you're trying to order things and you have things that look identical. So I have the example here, the word root. If we were trying to rearrange the orders of root, the letters in root, we have 2 O's, so you can't tell one O from another O. So they look the same. So what would happen is if you tried to write different combinations of, try to put them in different orders, is you would get some that look exactly the same, even though technically the 2 O's are different O's, but they look the same. And so we want to eliminate those that look the same, even if they are technically different from 2 different O's, because in the real life, what's the difference between, root with 1 O first versus the other O first? They look identical. We don't want to count those as separate. So we want them to be distinguishable. So we want a way to kind of eliminate those doubles that may show up if you tend to have more than one choice, or you can pick. So this is like if you can sort of pick something more than once. This would be if I was rearranging our O and T, but I could pick the O twice. And that would be the same as if it was like you had two O's here. That's equivalent. So it's not exactly a subset because we're using all of our letters here. But we do have to consider the fact that there are multiple combinations that, you know, we have to kind of divide by more things, because if you're not counting the things that look identical, you're going to have fewer objects or fewer possibilities. So this is we have to divide by more things. So we've got this formula with, again, you've got that factorial on top, and then we're dividing by factorials on the bottom, but we are grouping them by the number of things that are different. So in the word root, we have 3 different letters. So we're going to kind of group by, we're going to be dividing by the factorial for R, the factorial for O, and the factorial for T. And then the N that's in the bottom is going to be how many of those that letter appears. It will make much more sense when you see this. So we've got a series of letters here. We've got 3 B's and 5 T's. So there are 7 letters here. So our N is equal to 7. And I'm going to just label the number of B's we have are 3. And the number of T's we have are, that is not 7. I can't add. 8.
It's 8.
Yes. Don't know why I said 7. 3 plus 5 is 8. So
just to back up, so the 3 B's and the 5 T's that you got, like in the other example, you have Mississippi. The other, and prior to that, you had root. So are these just random letters that you picked?
Yes.
Okay,
yes.
Thank you.
Yeah, they're just random letters just to demonstrate this. So this would be, you know, something like this would be maybe if you don't have letters. Trying to think of a good example of this, because the way all the examples in the book use letters of words, you know, but this could be, let's say, I mean, you could kind of do it with license plates, but let's say that, you know, you can use the letter B only a certain number of times in a license plate or something like that. You know, there are some states that have certain rules about what letters can be used, and so that might be a situation where this occurs.
Okay.
So you've got how many things total you're trying to group together, which here we've got 8. And then we're also looking at the different categories of these things that we're trying to rearrange. So we've got 3 B's, 5 T's. So to use the formula, we have 8 factorial on top. And then you divide by the factorial of each of the groupings separately. So you have your division by the factorial on the bottom, but you're doing it by group. How many are in each group? So we've got 3, and then we've got 5. And there is no shortcut to this. You have to do the factorial stuff on your calculator. I mean, you could try to cancel things out. Like if out of the 8 factorial and then the 5 factorial, that would leave me with 8 times 7 times 6, because the 5 factorial canceled out. So, I mean, you could try to simplify it by 8 times 7 times 6, 3 factorials, 3 times 2 times 1. Like I can divide 3 times 2 is 6, so I can cancel those out. So you could try to reduce it before you know, get to the number, or you could just do all those factorials on your calculator. I wouldn't try to reduce unless you have small numbers like this, because it's just going to be too hard once you start getting really big.
Right. So is that 3 factorial times 5 factorial?
Yes.
Is that how am I reading? Okay.
Yes, these are multiplied. So let's see. So all I've left, I've reduced 8 times 7, which for whatever, I think that's 56. 8 times 7 is 1 that I just can never remember for whatever reason. Yes. I always want to say 54, and then I'm like, no, 54 is the 9 one. So like, I don't know why that one is just hard for me. But if you did on your calculator, if you did 8 factorial, which is a big number, divided by 3 factorial, and then you can also divide it by 5 factorial, you get the same thing. And my calculator allowed me to do that all at once. I just keep hitting divide after the factorial part, and I got 56. But so this tells us that there's only really 56 different ways to combine, to rearrange these sets of letters and have them look different.
But will they really look different?
They will, because we got rid of all the ones that don't look different. These kind of problems make me think of those. I think it's like, what is it called? It has the word mind in it, but you have like a combination of numbers and you're trying to guess the order of the numbers or something like that. And it tells you if you've got a correct number, and it tells you if it's in their correct spot, and you're trying to rearrange them. It just kind of reminds me of that. Like, how many ways can I rearrange these to figure out the code?
Right.
So the next example here, we've got Mississippi. So we've got how many letters in Mississippi? 1, 2, 3, 4, 5, 6, 11, I think. I want to double check that I counted that right.
I got 11 too.
All right. And now all of the different letters we have. So we've got the letter M.
One of those.
And then I, which is 1, 2, 3, 4. S.
Jeez. Go ahead.
Yeah, it doesn't really matter the order that we have them. I'm just doing in the order that I see them. So I've got 4 S's, 4 I's, 2 P's, and 1 M.
That's what I got.
Good. So the number of ways that we can recombine the letters in Mississippi and have actual different looking words. They're not forming actual words, but they could be gobbledygook words. So the M's, well, that would be 1 factorial. Then the I's is 4 factorial. Then the S's, 4 factorial. And then the P's are 2 factorial. So you're just, in the denominator, you're multiplying all of those factorials together. So 11 factorial is just going to be a giant number. But I did do 12 factorial earlier, so it's not going to be as big. But if you do choose to evaluate it.
I need a calculator that's easier to get to the factorial.
Yeah, I have to pick multiple. I have to hit 3 buttons. I think on your calculator,
I have to put the number, then hit math, go to the next screen, the probability screen, select number 4, which is the factorial.
Do you have the green little like diamond button on that calculator?
Diamond. There's some green letters on it. It's a TI 84 plus.
Okay. So I think I have a diamond button, and I think if I hit that and then the division, it gives me the factorial. But my battery apparently died on mine, so I can't verify. I was gonna pull it up, and I'm like, it's not turning on. But I know on one of the TIs there is a shortcut to get it.
Well, that 11 factorial, that's an ugly number.
Yes. Now 1 factorial is 1. 4 factorial is 24. And then 2 factorial is 2. So we're dividing this ugly number by 1 times 24 times 24 times 2. So if I just write this really ugly number, the denominator, when you multiply it, becomes 1,152. So our final number is 34,650. And I'm just going to run through all the factorial stuff to verify that.
I got
make
the
sure.
same number.
You got the same number. Okay, that's a
I
good
got the
sign.
same number.
I have been known to type things in the calculator wrong. So, all right. Yes, my calculator gave me the same thing. So that would be the number of, if you were trying to rearrange the letters in Mississippi, that's how many different ways you could do so with it, with them all looking different, which is a lot.
Yes.
So that was my last example, was the distinguishable permutations.
Okay.
So